Right. So here was the theorem that we proved yesterday, and just to recall, so we wanted to show that that you have a subgraph of GMP that's triangle-free and has more than half the edges is unlikely. Okay. And the argument was, given such a triangle-free subgraph of GMP, by the container theorem, that triangle-free graph has a fingerprint, which has the properties of the fingerprint. Fingerprint is small, and it maps to a container with few triangles. Okay, so there's a fingerprint which maps to a container. The fingerprint is small, and the container has few triangles. Okay. We apply supersaturation to the container to deduce that it has few edges. We apply Chernoff to bound the probability that. So we now want a probability bound. So what are the two unlikely events? So first, we know that S is contained in H and H is contained in GMP. So S is contained in GMP, and that gives us a factor of P to the E of S. And we also know that H is contained in G, the container, so G is F of S, and in GMP. That means that GMP intersect G has many edges. So and its distribution is binomial E of GP. And it's not hard to see that this is larger than the expectation using the fact that E of H is big and E of G is small. It follows this probability, this binomial, that this E of H minus E of S is bigger than the expectation, and therefore has probability exponentially small in the expectation. Okay. Okay. So this is the basic calculation that one does once you have a container theorem. We apply, and then so given this, so we apply Chernoff, and now we just take a union bound over fingerprints of the probability bound that we obtained. Okay. And a short calculation shows that this is small, exactly when you want it to be. Okay. Okay, so that was the idea. So now we're going to do the same thing, but in the setting of Ramsey's theorem. Is anyone any questions about this before I'm going to do basically the same thing again. Okay. Okay. So recall that Ramsey's theorem says that if you take a large enough clique and color its edges with, let's say, S different colors, then however you do it, there's always a monochromatic clique of size R, say. So R is fixed and N is large. And in the 90s, Rödl-Ruciński proved this famous theorem, which shows that even in GNP, if you color the edges of GNP with S colors, the same holds as long as P is bigger than this threshold, n to the minus 2 over R plus 1. Okay, this turns out to be the correct threshold. And this is the correct threshold basically because, so what happens at this point, the number of copies of KR in GMP gets bigger than the number of edges of GMP. Okay, so the number of copies of KR is like P to the R choose 2, N to the R. Number of edges is P times N squared. If you put those equal to each other, you get P equals N to the minus 2 over R plus 1. Okay, so this is the point at which, so if P is big, if it is smaller than this, you have fewer KRs than edges. So you can sort of understand it shouldn't be too difficult to color the cliques without making a monochromatic edge. It's not actually so easy to show that, but it is true. And they showed that if P is bigger than this, if you have more cliques than edges, then you can't color without making a monochromatic KR. So basically, the KR start interacting in very complicated ways, and there's no way to avoid it. But it's not so easy to prove. In fact, it's quite hard to prove. But luckily, Nenadov and Steger found a lovely way of deducing this theorem from the container theorem. So I'm going to give you that argument. Okay, but let's just work in, since I don't really want to think about the conditions for the hypergraph container lemma for k uniform hypergraphs. Let's just think about the case R equals 3, the proof is essentially identical. Just there's a tiny extra calculation you have to do. Okay, so all the ideas are already in the case of the triangle. Okay, so what we want to do is apply the container lemma to the three uniform hypergraph, not the one that encodes triangles in the complete graph. We want a hypergraph that encodes monochromatic triangles in S colorings of the edges of the complete graph. Okay, that sounds a bit more complicated. It's only very slightly more complicated. So what would this hypergraph be? Well, all we do is take S copies of the hypergraph that encodes triangles. Okay, one for each color. Okay, so a subset of the vertices of this hypergraph corresponds to, I guess, a multi-coloring of the edges of the complete graph. Right, so if you take the whole thing, it's like you're saying each edge can be any of these S colors. And an S coloring would be, you know, it would be sort of, you take, for each edge, you take exactly one of the copies. So this this hypergraph has S times n choose 2 vertices and S times n choose 3 hyperedges. Right? It's just S copies of the one we had before. Okay. And so note that if you have an S coloring of the edges of Kn with no monochromatic triangle, that is still an independent set in this hypergraph. Right? For each edge, you have a color, so you take the corresponding vertex. So you take the edge in the corresponding copy of Kn, so the vertex in the corresponding hypergraph. Right? So in other words, so in each copy of this, so in each of these S copies, you take, in the first one, you take the edges of color 1, in the second one, you take the edges of color 2, and so on. And finally, the edges of color S. And if you have no monochromatic triangle, each of these graphs is triangle free, so each of them is an independent set. And because the hyperedges are all inside the copies, it's an independent set in the whole thing. Is that clear? There appears to be some building work outside my apartment. I hope you can't hear it. Okay, so just like before, our average degree is about n, and our tau is n to the minus a half in the container lemma, because it's just S copies of the same thing. So it's just exactly the same calculation. Okay. Okay, so what we need is a supersaturation theorem. Okay, so here's the supersaturation theorem that we need. So for every S, so we'll see in a minute why this is the right thing. For every S is a delta. So if n is large, G is a graph with n vertices, and density at least 1 minus delta, then every S coloring contains many triangles. Okay. So why is this true? Well, it's not so difficult to prove. If anyone wants to suggest something. Well, first, how do you find one triangle? Well, that's easy. You just use Ramsey, and it doesn't really matter that there's if there's only 1 minus delta proportion of the triangles. You just sort of you take a vertex of high degree, look in the neighborhoods. One of them must be dense and large. Go into there and repeat. Okay, so just the usual proof of Ramsey theorem with you have to be slightly more careful just to keep the density high, but it's not so difficult. And then, how do you find many? Well, we saw in the exercises on Monday how to prove a supersaturation theorem for Mantell's theorem. So there are various ways to do it, but one simple way is just to look in each sort of large constant size subset, and then typically in there you'll see the same properties. So if you look at a random subset of the vertices of constant size, then sort of most of those will be pretty dense. And so by the proof of Ramsey, you'll be able to find a monochromatic triangle inside there. And then by double counting, you see that actually if this happens most of the time, then you must get the correct number of triangles. Okay, so this is a very useful idea. I tried to emphasize this in the exercises more than in the lectures. That the proving supersaturation theorems is often quite simple. You just take a random subset, find a copy in there, and double count. This is sort of a simple, very useful general way to prove supersaturation. Did that make sense? Okay, so if not, sorry, I encourage you to sort of work out the details of that. It's a nice exercise. It's not difficult, and it's a very useful idea. Okay, so using the container lemma and the supersaturation theorem, and using the usual method, we obtain the following container theorem for triangle-free colorings. So for every S, there's a delta. There's a collection of containers and a function. And the containers have the following property. So each of them, so this is somewhat different to before, each of them has at most 1 minus delta times n choose 2 edges. Okay, so we'll see in a second why. I'll try and explain how you get this. And for each S-colored graph with no monochromatic triangle, there's a small fingerprint and which maps to a container for this this S-colored graph. Okay. So what is going on here? What happened? So we had this hypergraph that was S copies of the complete graph. When you apply the container lemma to that hypergraph, you throw out a positive proportion of the vertices. So what you end up with is some subset of each graph. So a collection of S graphs. Okay, and I'm thinking of this container as being the union of those graphs. Okay, and as long as in that union of graphs there are many monochromatic triangles. Sorry, so you just have a bunch of graphs, and then in each one you look at the triangles. If there are many triangles overall, constant proportion of n, so constant times n cubed, then you can apply the container lemma again. Right, so remember when we were applying the container lemma, this is some time ago, that as long as we've kept a constant proportion of our hyperedges, then everything just works the same and you can apply again. Okay, the bounds still hold with a different value of c. Okay, so as long as you still have a constant proportion of your hyperedges, you can keep going. So when we finally have to stop, and in each step, we're only producing a fingerprint of size n to the 3/2, because remember our tau was n to the minus a half, and our number of edges is order n squared. Okay, so that's why we gain the fingerprint of the right size. So the only question, the only difference is when do we stop? And we stop when our supersaturation theorem fails. Okay, so we can keep iterating the container lemma until our supersaturation theorem fails. And what did our supersaturation theorem say? It said as long as the union of the edges of these S graphs covers 1 minus delta proportion of the edges of the complete graph, then we have many monochromatic triangles, and therefore we can continue. So that the supersaturation theorem only fails, the assumption only fails when the union of our S graphs, of the S different colors, has fewer than 1 minus delta times n choose 2 edges. And that's why we have this condition. We can continue until each container, meaning the union of the colors, has at most 1 minus delta times n choose 2 edges. Okay, And that's what I mean by this. This graph is contained in it. So this is an S-colored graph. I is just a graph coming with an S coloring, and I is a subgraph of the corresponding container. Okay? So this doesn't look very strong. And this is the beautiful idea of Nendorf and Steger, is that this is enough to show that this is unlikely. Okay? So why is that? Okay, so suppose there exists an S coloring of the edges of GMP with no monochromatic triangle. So our job is to show this is unlikely. We have to use the container theorem to show that this is unlikely. Well, by the container theorem, GMP contains a fingerprint. So I contains a fingerprint, which is then contained in GMP. And then what's the point? The point is that I is just an S coloring of all of the edges of GMP. So if I is contained in f of s, then GNP is contained in f of s. Right? So now we've thrown out I, we just know that S is contained in GMP, and GMP is contained in f of s. So the whole random graph is contained in this container. And f of s has at most 1 minus delta times n choose 2 edges. So what's the unlikely event? What's the probability of this occurring for a given S? I think I'm actually going to let you think about this for a minute, and I hope someone answers it. What is the probability for so given S is given to us. We can take a union bound over S afterwards. What is the probability of this event at the bottom of the screen? S is contained in GMP, which is contained in f of s, when E of f of s has size at most this. I want to bound on this probability.
Exponentially small.
Sorry, I can't hear.
Exponentially small in Pn squared.
Yeah. But more precisely. So what are the there's two terms. So to give you a clue, there's a p to the something and a 1 minus p to the something. So what are the two things? P to the what?
P to the size of s. Ooh, wow.
P to the size of s, exactly. And 1 minus p to the power
delta.
Yeah, exactly, right. So S is contained in GMP. That has probability P to the size of S. GMP avoids everything. Does anyone not in f of s is a non-edge of GMP. And there are delta n choose 2 of them. So, sorry, we're back here. So we're here now. There's probability P to the E of S times 1 minus P to the delta n choose 2. Right? Because every non-edge of f of s, every guy who's not in f of s cannot be in GMP. And f of s is a fixed graph. It's a fixed container. Right? So we're summing over s, and therefore f of s is fixed for each s. Okay? And now it's just the same thing. Sum over the size of s, sum of the choices of s given its size, p to the s, 1 minus delta to the same, 1 minus p to the same thing. Same calculations before. So n squared choose s is the most e times n squared over s to the s. Pull the p inside. Use 1 minus p as the most e to the minus p. Just the usual stuff. And this is small because p is bigger than 1 over root n. Okay. So it ends up with, by this point, we've reached exactly the same calculation, basically, or by this point, perhaps, right? With exactly the same expression. Okay. So I hope I managed to get across the beauty of that proof. I was really extremely impressed by how lovely and simple it was the first time I saw it. Okay, so I'd like to make an observation about this. So if there are questions about this, then please say. So note that this not only goes to 0, but it goes to 0 exponentially fast in Pn squared. right? This term is beating this term by a lot, or so by sort of a decent amount. So the bound that you get is not just little o1, it's like e to the minus order pn squared. Okay, e to the minus delta over 4 times pn squared, if you like. Okay. Right. Are there any questions about that? So, okay. So if not, then let's see a nice application of it. So an old theorem of Nešetřil-Rödl, which says that there exists a kr plus 1 free graph such that any S coloring of the edges contains a monochromatic kr. Okay, and this was actually one of the motivations for Rödl-Ruciński studying this problem. So how can we find such a graph? Well, okay, we just proved something about GMP, so you might guess that we're going to do it randomly. So what do we take for GMP? These slides I think are not quite in the right order. I should have reorganized them. Right, so how can we, so we're going to take GMP, and we want to take P such that we can apply the Rödl-Ruciński theorem, right? So the Rödl-Ruciński theorem said, we're back here, that so if P is bigger than n to the minus 2 over r plus 1, then GMP is a good candidate because every S, so GMP really does arrow KR. So if we're going to apply this theorem of Rödl-Ruciński, we need to take P bigger than n to the minus 2 over r plus 1. Okay? And if we're lucky, this graph won't contain any KR plus 1s. But how many KR plus 1s do you expect to find? Well, unfortunately, above this threshold, you expect to find at least n copies of KR. So at first glance, this doesn't look very promising, right? So in order to take P big enough, so I'll come back here. In order to take P big enough so that we can guarantee this happens, GMP will typically have about n copies of KR plus 1. Actually, more than n. So what should we do? Well, here's the lovely idea of Rödl-Ruciński. So if you just apply Harris's lemma, also known as the FKG inequality, so the probability that GNP is KR plus 1 free, it's not large, but it's not crazily small. Because the expected number of KR plus 1s is about n, the probability it's KR plus 1 free is roughly e to the minus n. Okay, so just because the KR plus 1s are all positively correlated. Okay, that's what Harris's lemma says, that increasing events are positively correlated. Okay, but that's very small. E to the minus n is very small. So it's smaller than the number of, well, okay, not smaller than the number of graphs, but yeah, it's pretty small. But luckily, we proved the probability that GMP does not arrow KR, that there exists an S coloring that avoids a monochromatic KR, is e to the minus order Pn squared. And that probability is much smaller than e to the minus n. Right? So the probability that we're KR plus 1 free is tiny, but the probability that we fail to arrow KR is even smaller. So the GMP has the two claimed properties with positive probability. Right? You have some tiny probability of being KR plus 1 free, but some even tinier probability of failing the thing you want. And therefore, you must have positive probability of them both occurring. Okay. I also found that extremely beautiful and surprising when I first saw it. Okay. So, are there any questions about that? If not, then I'll go on to the.
No, but that means that you can take kind of any p here which is bigger than root n. I mean, 1 over root n, right?
Take any p bigger.
Like any p would work over, which is larger than 1 over root n, right?
So you can make it a little bit bigger, but you can't allow. So if p gets bigger, then this probability e to the minus n gets smaller.
Right. Yeah.
And it gets smaller like p to the r plus 1 choose 2 times n to the r plus 1. So so at some point it will fail. So it'll work. It works in some range. You can make it a bit bigger, but not a lot bigger. Yeah. So it works for say p to the you multiply by n to the epsilon or something, but or n to some small constant. But yeah, you couldn't take p constant, for example. Yeah,
sorry.
Because this probability doesn't get any better than this. It's just it's only going up linearly in p, whereas this is going down by some polynomial.
So this implication was known before. I mean, this is not new, right?
Sorry. This appears in the paper of Rödl-Ruciński in '95, and so I don't know exactly how old it is. I don't know if even say Nešetřil-Rödl knew this implication. We just couldn't prove the theorem. But yeah, this is at least goes back to Rödl-Ruciński. Yeah. And possibly further. Okay. Right. So now, I'll skip past this. Sorry. So now I'll skip to the other lectures. Right. So now you have you're in a position to also to do the first exercise from yesterday. So the idea was that to do this for KR, then you just need to run through the argument again, changing little things. Okay. Sorry. Let me open. Where is it? Lecture 3. There we go. Okay. So now we're ready to start today. Right. So I guess we'll only get through half of today, but that's also fine. Okay. So what have we done? We have stated this container lemma for k uniform hypergraphs. So again, if you find this just extremely confusing, then don't worry too much about it. The only thing you really have to remember is you have a k uniform hypergraph. You have some funny condition on the degrees, which says that the edges are sort of reasonably nicely distributed. And you should think of this condition as being this is the condition that's satisfied by the hypergraph encoding copies of H in the complete graph at the right threshold. So this is just some funny condition that encodes the thing that we want in our applications. Okay. Then there's a collection of containers with the following property. Every independent set in our hypergraph has a fingerprint that's small and which maps by this function to a container for the independent set, right? And each container is, you get to throw out a positive proportion of the vertices. So iterating this container lemma, you end up with container theorems that you like. Okay. Okay. So to get a hang of this, I suggest doing some exercises. So running through some simple applications, checking these conditions, how they work for particular hypergraphs, and practicing iterating it to give container theorems. So it's the kind of thing that it seems weird at first. So I mean, in that sense, a bit like the regularity method. When you first see the regularity lemma, it seems extremely complicated, and every application seems difficult, and there's all these crazy constants flying around everywhere. But actually, once you get the hang of it, it's just something where you say, okay, you apply it, and it obviously gives this, and okay, there's some details you work out later, but they're always the same. Okay, so yeah, so you shouldn't be too sort of scared by the technicalities. It's not really that technical. Okay. Okay, and so just remember the applications. So we proved this container theorem for triangle free graphs, which proved the Rödl-Ruciński theorem, the sparse Mantel, and we just saw this application for triangle free colorings, which implies this theorem of Rödl-Ruciński. Okay, so plan for today, or at least the next sort of 20 minutes. So I'm going to try and talk about counting H-free graphs, where H is a bipartite graph. So we're going to talk, I'm mainly going to focus on this old theorem of Kleitman and Winston, which, as I mentioned, was sort of the key first step in all of this, this story, which is counting number of C4 free graphs. But I'm also going to would like to discuss a sort of a more general result, recent result of Ferber, McKinley, and Samwarty. And then, so I won't do this today because there isn't any time, but tomorrow I'll talk about this this geometric theorem of Balog and Sholem-Moshe. Okay, so it's an application to combinatorial geometry or discrete geometry. Okay, so so question: how many H-free graphs are there on n vertices? This is a very sort of basic question from graph theory. Okay, so so who can give me an easy lower bound and easy upper bound? So the lower bound is perhaps easier.
All graphs with less edges.
Say it again.
All graphs which have less than the number of edges of H.
Oh yeah. So
right,
but we can do better than that. Yep, that's a lower bound, but you can do better.
2 to the extremal number.
Yeah, 2 to the extremal number, right? You can take any extremal graph and then take all subgraphs. And how about upper bound? So I thought for a second that you were answering that question, if that's a hint.
So 2 to the n squared, something like that?
Right, so that is an upper bound, but we can do better than that.
You take the blow up of a complete graph which has less parts than a chromatic number.
Right, so that would give the lower bound basically.
Oh yeah, sorry, yeah, go ahead.
Yeah. So the upper bound, I mean, so again, it's using the extremal number. So any graph with more than the extremal number is not H-free. So you definitely can't have more than all graphs with at most the extremal number, which you can bound by essentially n to the extremal number. Okay, so the lower bound is take a single extremal graph and look at its subgraphs. The upper bound is look at all graphs with at most the extremal number. Okay, and these give things bounds that look basically pretty similar, right? 2 to the extremal number and n to the extremal number. That's not too bad. Okay, but we'd really like to know which is correct. And Erdős, Frenkel, and Rödl showed in the 1980s. This is a fairly easy application of the regularity lemma, though I'm not sure if that's how they did it actually. That the lower bound is basically correct for non-bipartite graphs, right? This little o(n) squared in the exponent is small compared to the extremal number as long as H is not bipartite. Okay. For bipartite graphs, it's quite a bit more difficult. And Erdős asked a long time ago if the lower bound is basically correct for every bipartite graph containing a cycle. So he conjectured it's true for all bipartite H containing a cycle. If H is a tree, then the upper bound is correct by some simple counting. Okay, or at least sometimes. Right. Okay, so the first result in this direction was actually before Erdős, Frenkel, and Rödl. So this this conjecture of Erdős was proved to be true for perhaps the simplest bipartite graph, the cycle on 4 vertices. Okay, or the simplest bipartite graph that contains a cycle. Okay. Then there was a long gap before Balog and Samwarty proved extended this result to KST free graphs. Though note that this is only gives you the edge conjecture when we know a corresponding lower bound, right? So this n to the 2 minus 1 over s, it's known to be the correct order when t is bigger than s minus 1 factorial. Okay? But this Balogh-Samity paper was extremely important in the development of the container method. You should think of this as being sort of the first hypergraph container lemma, in some sense. And then with David Saxton, we proved a corresponding theorem for graphs avoiding even cycles. And then, I mean, it appeared somewhat recently, though this was proved a few years ago. Ferber, McKinley, and Samwarty gave a really beautiful argument that I'll discuss, essentially proving the edge conjecture, but not quite proving it, so subject to some annoying technical condition. So if it's true that the extremal number is of order n to the alpha for some alpha, then they prove the conjecture. It's thought that every bipartite graph has an extremal number of this form, but it's not known. Another condition that was enough that if basically the simple random lower bound, so take a random graph and kill all the copies of H, if that fails, so if you can beat that by n to the epsilon, then it's also true. But that's also only known in a few cases. So this edge conjecture is almost proved, but there's still some work to do. Okay, and all the proofs use some kind of containers. So Kleitman and Winston is sort of the first container type result, so graph container type result. Balogh-Samity is the first sort of hypergraph container type result, and then these later two papers use explicitly the container lemma. Okay, so let's sort of sketch the proof of, so actually only of Ferber, McKinney, and Samwarty. I'll just say a few words maybe if there's time about my result with David Saxton. Right, so we're going to prove the following container theorem, sorry, I should say. Okay, so we're going to deduce Kleitman-Winston from the following container theorem that says, so for each k, so k needs to be bigger than some large constant. There's a collection GNK of this many graphs, each one with at most k times n to the 3 over 2 edges, and which cover the C4 free graphs. Okay, so this is a slightly different kind of container theorem, and we're going to prove it in a slightly different way than the previous than we did in the previous applications. Okay, so this is sort of a quite important technique of applying the container lemma that I'm going to discuss. Okay, so why does this imply Kleitman-Winston? Well, just take k to be a large constant. If k is a large constant, then what do we have? Each container has big O n to the 3 over 2 edges, and the number of containers is also big O n to the 3 over 2. So if you sum over containers, the subgraphs of those containers, you get something of the form 2 to the big O n to the 3 over 2. Make sense? So there's 2 to the constant n to the 3 over 2. So 2 to the constant n to the 3 over 2 containers, and each one has 2 to the constant n to the 3 over 2 subgraphs. Okay, when k is a constant. This container theorem is true for all k bigger than a constant, or bigger than some large constant, and this is going to be useful for some other application that I'll try to discuss. Okay, so how are we going to prove such a container theorem? Okay, so here's just the same thing, but slightly more precisely. Now I've written there's constants k0 and c such that this holds if k is bigger than k0. Okay. So we're going to apply the container lemma to some hypergraph. So which hypergraph do we want to apply it to? The natural candidate is the hypergraph that encodes copies of C4 in the complete graph. Right. So that's just the same as before. So it's all the vertices of the edges of the complete graph, and the hyper edges are 4 edges that form a cycle. Okay. Right. Okay. So what's the value of tau that we need to prove this container lemma? So remember, the number of containers that you get in a given step is something like the number of vertices in the hypergraph choose tau times the number of vertices in the hypergraph. And in a given step of this this application, so what are we doing? We start out with this hypergraph on the edge set of the complete graph. We apply the container lemma, and we're going to throw out a constant proportion of the vertices, so of the edges of the complete graph. So we go down to 1 minus delta times n choose 2, then 1 minus delta squared times n choose 2, and so on and so on and so on and so on. But we don't want to stop until our containers have k times n to the 3/2 edges. Okay, so we have to go for a really long time. We don't just go for a constant number of steps. We need to keep iterating for like log n steps. And as we iterate, as our containers get smaller, our tau is potentially going to change. And so our number of containers that we produce in each step is going to change. Okay? So we need to know that at the point when we have, say, k times n to the 3/2 edges left in our container, so a hypergraph we're working on is the induced subhypergraph on that graph. So the vertex set will be the edges of our graph, of our current container, and the hyper edges will be C4s inside there. We need to know what the tau is for that hypergraph. Okay? So the hypergraph we're working on midway through this process, it's an arbitrary graph with k times n to the 3/2 edges. And the hypergraph is all the C4s inside that graph. Okay? Okay. So I claim, so the number of containers that we'll get is E of G, number of vertices in a hypergraph, choose tau times E of G. And if tau is 1/k to the 4/3, well, E of G is kn to the 3/2. So then tau times this will be n to the 3/2 over k to the 1/3. And so E of G choose tau times E of G will be of the correct form, the form we want. Okay, so this takes maybe a little calculation to really prove properly, but it will be sufficient to show that tau can be taken to be 1/k to the 4/3. Okay, when G has k times n to the 3/2 edges. Okay. Right, and perhaps you're worrying a little bit that I'm throwing away a log n. So if you're really on top of this, then that would be your question. And the reason you don't get an extra log n is because as you apply this going down, you're only applying it. So this bound is getting worse very quickly as k decreases. And because you're taking a product over an exponentially decreasing set of k's. And if you take a product of this thing over an exponentially decreasing set of k's, it turns out it's only the last one that really matters. Okay, so but if you didn't understand that, don't worry. But just a technical point, this is just to explain why this is really the thing we want to get, that we don't get extra log n here. But if you're not worried about log n's, then, well, you need to be worried about log n's in this application. But perhaps don't worry. So it turns out that by a not too complicated calculation that I don't really want to go into the details of, a tau of this order is enough. Okay.
So Robert, it doesn't mean that the tau matters so much here, right? Because just give you like this constant of, I mean, the change.
Right.
So.
Yes. Sorry, that's an excellent point. So to prove the container theorem I stated, then we need tau to be 1/k to the 4/3. But for the application, you're exactly right. Anything of the form k to the minus alpha, with alpha strictly bigger than 1, would be enough.
So, but you say like tau is kind of the right tau in terms of like if you think of it like like this random?
No, so there's two different questions. So there's one is what is the correct tau, meaning the best possible one, and the other is what you need to prove the application. So the correct tau turns out to be 1 over k squared, and that's what I proved with David. That so we proved 1 over k squared. But the lovely idea of Asaf and Gwen and Wojtek was that that not only do you not need that k squared, you only need k to the 1 plus epsilon, but also you can prove that in a very simple way that generalizes to every bipartite graph.
Right, so I mean this k over 4/3 is kind of in the middle of.
Yeah, k over 4/3 is just what happens to fall out of the supersaturation theorem that I'll prove next, or state or whatever. Yeah.
Right, but in your paper you said what k squared or.
Yeah, so with David then we proved 1 over k squared, and that's optimal. That gives that can't be beaten. There's a construction that shows that you can't do better. Yeah, but for a general bipartite graph, it's not clear what the correct thing is. So for C4 and in general for even cycles, we got we got the correct thing, assuming that the extremal number is given by the upper bound. So for the even cycles for which we know a corresponding lower bound, that is C4, C6, C10, then it's correct.
Sorry, Rob, but that means, I mean, typically when you see this container application, you would expect the analysis going down to like 1 plus epsilon times the extremal number. But you say what you're saying
right.
Before is not the case. Like
yeah, no. So here it fails at large constant times the extremal number.
So this you cannot expect to go like 1 plus epsilon.
Right, and in fact, so if you were hoping, yeah, so for these we can't hope to go all the way down to 1 plus epsilon. And also the counting problem is false in general for 1 plus epsilon. Right, so with David we gave a counterexample for C6, a construction for C6 that showed it fails. Excuse me. Yeah, so right, so absolutely, it's a very good point. So we're only going down to a large constant times the extremal number. Absolutely. Yeah, and proving supersaturation below that is difficult and not even clear that it's true. Right. So the idea that I want to get across, and I see that I'm basically out of time, is this concept of a balanced supersaturation theorem. So so far we've always used supersaturation theorems to control our containers. And one of the key ideas, and it's been in my paper with David, is that what you actually want here is not just have many copies of C4, but you want to force them to be balanced in some way. And you can't guarantee that that's true for if you look at all C4s in G. But we don't need to look at all C4s. We just need there exists a collection of C4s in G, such that, okay, there are reasonably many of them, but they satisfy these nice kind of balance conditions. So no edge is used in too many copies of C4, and no pair of edges is used in too many copies of C4. Okay? So the key idea here is that you don't just take all of the C4s, you take a particular clever subset of them, subcollection, which have these nice properties. And the thing that really restricts you is to do with the number of the number that you're forced to contain a pair of edges. So when you're calculating your tau, at the beginning it's sort of delta 4 that hurts you. Delta 4 is 1, but later on, after you've iterated a lot of times, once you get down to something that's say smaller than n to the 5/3 edges, then it's your delta 2 that really controls your tau. So just to see that, so our average degree is k4, is k to the 4. Our delta 1 is k to the 4 by a. our delta 2 is like 1 over k squared, which actually turns out to be the sort of this is the thing that you sort of can't avoid. The delta 3 is also 1 over k squared, but for this particular supersaturation theorem, the delta 4 still gives you k to the 1 over 4/3. So, so this is the supersaturation theorem of Fairbairn, McKinley, and Samorty, which is a bit weaker than the one my paper with David Saxton, and this gives you this is why you get a tau of k to the 4/3. So in particular, they don't get as many copies of C4 as you could potentially. Okay, so this is all very quick because I'm just trying to wrap up. So you get your tau is k to the 4/3. So it's enough to prove this balanced supersaturation theorem. And perhaps because I'm running out of time, I'll talk about that tomorrow. So I'll pick up at this point tomorrow and talk about how to prove such a balanced supersaturation theorem.